Hi everyone. In this talk, I'm going to describe a version of the Friedland Hayman inequality for convex cones. This is joint work with David Jerrison at MIT and Sarah Rayner at Wake Forest. Before I begin, I'd like to thank the organizers, Shiza, Dima, and Emilio for giving me the opportunity to present this work at this conference. So let me begin by describing the original Friedland Hayman inequality. So this inequality concerns the growth rate of two homogeneous harmonic functions which are defined on complementary cones in Rn. So in the two-dimensional picture, we have two cones centered at the origin, and then we have two functions, u1 and u2. So u1 is strictly positive inside the cone, where u2 is identically equal to 0. And then outside, or in the complementary cone, we have the opposite situation where u1 is identically 0 and u2 is strictly positive. And since we're requiring that u1 and u2 are homogeneous harmonic functions of positive degree, then up to multiples, there's a unique such function, u1 and u2, with respect to these cones. So then the Friedland Hayman inequality says that if we denote the homogeneity of the two functions by alpha1 and alpha2, then the sum of the homogeneities is always greater than or equal to 2. And moreover, since we can think of, once we're given a cone, u1 and u2 are unique up to a constant multiple, these characteristic exponents, alpha1 and alpha2, are really associated with the cone itself. So as well as the inequality, which was proved by Friedland and Hayman in the 70s, the case of equality has also been established, where equality in this theorem holds if and only if u1 and u2 are at least up to a constant multiple, the positive and negative parts of a linear function. And in particular, what that means is that after a rotation, we have that our cone must, or our two cones must just be two half spaces. And then our functions u1 and u2 are just some multiple of, after this rotation, the x1 variable. So later in the talk, I will say a little bit more about the proof of this theorem and the proof of the case of equality in the theorem. But let me just say for now that an important step in both the proof of the inequality and equality is Sperner's rearrangement theorem on the sphere, which essentially reduces the problem rather than studying all cones or all complementary cones in Rn to study a particular class of them which are generated by spherical caps. But I'll be saying more about the proof later in the talk. So one important application of this inequality was carried out by Alt, Caffarelli, and Friedman in the 80s when they were looking at a class of two-phase free boundary problems. So what they showed was that if we define this functional phi of t for given subharmonic functions u1 and u2, then this functional involving the gradient of these subharmonic functions is a monotonically increasing function of t. And to prove this, they directly used this Friedland Hayman inequality. And in particular, this monotonicity holds in the following setup, where we have one function, say u, which is equal to 0 on some curve, or more generally some hypersurface. And then u1 and u2 are equal to the positive and negative phases of this function, where we're assuming that the function u is harmonic anywhere where it's not non-zero. In other words, anywhere away from this hypersurface where u is equal to 0. So it turns out that the class of two-phase free boundary problems that they were looking at, the minimizer of this variational problem precisely has this structure, where it's harmonic in its two phases, where the minimizer is positive and negative, and then it's separated by what is called the free boundary, where the minimizer vanishes. And in particular, they use the monotonicity of this functional phi of t as t goes to 0 to establish that the minimizer of the free boundary problem was Lipschitz continuous in the interior of the domain where the minimizer was defined. And in fact, they also used the case of equality in the Friedland Hayman inequality to obtain further regularity of the minimizer. And in fact, they used it to show that the free boundary, the set where u is equal to 0, which a priori has no regularity, is in fact a smooth hypersurface within the domain. Okay, so let me now say a little bit about our version of the Friedland Hayman inequality. So in our case, we start with a convex cone gamma in Rn. To say gamma looks something like this. And then we have that gamma is containing two disjoint connected cones, which we're going to call gamma plus and gamma minus. So in the two-dimensional picture, we have something like this. In higher dimensions, we have the same setup, but we don't require that gamma minus and gamma plus are necessarily convex subsets of gamma. Right? All we require is that we have a convex cone, and then we have two disjoint connected cones within. So what do we do with these cones? Well, we now consider, just like in the classical case, harmonic homogeneous functions which are supported on these two cones, gamma plus and gamma minus. And then we impose some boundary conditions to these harmonic functions. And what do we impose? Well, we impose that u plus and u minus vanish on the common boundary between gamma minus and gamma plus, very analogous to the original inequality. And then on the part of the boundary consisting of the original convex cone gamma, then we impose these Neumann conditions. So here, u is the outward normal. And we impose that the normal derivative in u plus and u minus vanish on this part of the boundary. Okay? And again, just like in the previous case, these boundary conditions and u being a harmonic function of positive homogeneity ensures, again, up to a constant multiple, there's only one such function on these cones, gamma plus and gamma minus. And in particular, there's only one such positive homogeneity, which we're calling alpha plus and alpha minus. So then the theorem that we show is that the same inequality, alpha plus alpha minus, the sum of these homogeneities, is still greater than or equal to 2 in this more general case, where we have our convex cone gamma. And moreover, we classify the case of equality to be any time when our original convex cone gamma contains a line, or in other words, contains a copy of R. Right, so again, in the two-dimensional picture, what that means is that our cone gamma is either a half space or the whole of R2, and then our disjoint connected cones gamma plus and gamma minus are just the two halves of our half space. Okay. In higher dimensions, there are many, many more cones gamma containing a line, and in any of those cases, we can find these connected cones gamma plus and gamma minus leading to equality in this inequality. So when gamma is equal to Rn, then this is precisely the statement of the original Friedland Hayman inequality. Okay, because then we don't have any Neumann conditions to impose, and we just are precisely back in the setting of the very first slide. Okay, and moreover, when gamma is a half space, then we can reflect over the Neumann boundary to get a problem again on the whole of Rn, and then again we're back in the setting of the Friedland Hayman inequality. Okay, but for a general convex cone gamma, there's really some work to be done in order to show that the same inequality holds. So why were we interested in proving such a variant of the Friedland Hayman inequality? Well, the main reason for us is that we're again interested in these two-phase free boundary problems. And it turns out that if you want to establish the Lipschitz regularity up to the boundary of such a problem, then to adapt the Alt-Caffarelli-Friedman approach, in other words, to adapt or to find a functional that we can prove is monotonic, then we end up needing precisely this version of the Friedland Hayman inequality, as opposed to the original one that they used. And in fact, with David Jerison and Sarah Rayner, we carry out such a process, and we find a class of convex domains and associated two-phase free boundary minimizers, and we use this inequality to prove that the minimizer is indeed Lipschitz regular up to the place where the free boundary meets the fixed convex boundary. Okay, so let me now say a few words about the proof, both of our inequality, and as we go along, we'll also see how the proof of the original Friedland Hayman inequality works. So the first thing to notice is that in 2 dimensions, then given such a cone gamma and given associated cones gamma plus and gamma minus, which are disjoint, one can do a calculation to explicitly write down the corresponding homogeneous harmonic functions. And then checking the inequality turns into a not so difficult calculus exercise to show that given any such cone in 2 dimensions, when we add them up, we always get something that's greater than or equal to 2. So the 2-dimensional case can really just be done by hand and explicitly see that such an inequality holds. And moreover, if we know the inequality in a higher dimension, then it's automatically going to imply the inequality in a lower dimensional space. And the reason being is that given any cone in, say, dimension n, we can think of it as being a cone in a higher dimension just by adjoining copies of R. Okay? Or on the level of the harmonic functions u plus and u minus, if we have a function u plus of x defined on a cone in little n dimensions, then we can just trivially extend it to a cone in a higher dimension, as we see by just adjoining copies of R. And by doing this, we're not changing the fact that u plus is a harmonic function, and we're also not changing the homogeneity of the function u plus. So what this means is that if we can prove the inequality in a higher dimension, then for free, we get all the lower dimensions below it. Or another way of saying that, it tells us that this inequality is getting stronger as we move up in the dimension. That somehow this inequality should be getting harder to prove as the dimension increases, because each time we increase the dimension, we're getting all the lower dimensions for free somehow. So how do we use this fact? Well, the way that we use this fact is that we, in a careful way, take the limit as this dimension capital N goes to infinity. Okay? And what we find is that with a careful rescaling, one obtains in the limit a relationship between our homogeneities alpha plus and alpha minus and an associated extremal eigenvalue problem with a Gaussian weight. So in our proposition, and this is a very, very analogous proposition to what was proved, what was used by Beckner, Koenig, and Pfeiffer when they proved the case of equality for the original Friedland Hayman inequality. What we show is that the homogeneities alpha plus and alpha minus are bounded from below by the first eigenvalue of a Gaussian eigenvalue problem. So in this case, we have our cone gamma, and then within it, we have our 2 subcones, gamma plus and gamma minus. Okay, and then we're imposing that our test functions in our Gaussian eigenvalue problem satisfy that f is equal to 0, or the test functions vanish on the common boundary between gamma plus and gamma minus, and then we leave them to be free on the Neumann part of the boundary. Okay, and then we get this relationship that bounds from below alpha plus and alpha minus in terms of this Gaussian eigenvalue. So if we call this infimum lambda of gamma plus and gamma minus, then what this proposition tells us is that if we want to get a lower bound, and remember the lower bound we're aiming for is alpha plus alpha minus is greater than or equal to 2. If we're looking to get such, oh, sorry, that should be an alpha minus. If we're looking to prove such a lower bound, then it's sufficient to prove a lower bound on the sum of these Gaussian eigenvalues instead. So the desired inequality that we need to prove is that lambda gamma plus lambda of gamma minus is greater than or equal to 2 whenever gamma plus and gamma minus are disjoint cones in our fixed cone gamma that we start with. So in the case where gamma is equal to the whole of Rn, Beckner, Koenig, and Pfeiffer had this an analogous proposition to the one above, and then they used a Gaussian rearrangement theorem to reduce to the case where gamma plus and gamma minus are not general cones in Rn, but instead are half spaces. So what they wanted to show was that lambda of, say, H sub S plus lambda of H sub S minus is greater than or equal to 2 for all S, where HS plus and HS minus are just meant to be half spaces separated by the hypersurface when X1 is equal to S. So in other words, this Gaussian rearrangement theorem allows them to essentially reduce the problem to a 1D problem, where the only variable they have to care about is this S variable, which is telling us where on the X1 axis we're separating our two half spaces. And then they were able to establish bounds on these Gaussian eigenvalues for these half spaces to show that this inequality does indeed hold. And moreover, one only gets the equality when S is equal to 0, and these two half spaces are separated exactly at X1 equal to 0. So this was how they proved the original Friedland Hayman inequality and characterized the case of equality as a result. So unfortunately, in our case, when gamma is just a general convex cone, we don't have the corresponding rearrangement theorem. So we can't make the same argument directly because we have no way of rearranging gamma plus and gamma minus in such a nice way when they're subsets of this fixed cone gamma rather than the whole of Rn. So how do we get around this? Well, to get around it, instead what we do is that we try and bound our eigenvalues lambda of gamma plus and gamma minus in terms of Gaussian eigenvalues on complementary subsets of Rn. So to do this, we use Brenier's optimal transport mapping, where we map between Gaussian measure on Rn, which is somehow the setting of the original inequality, and Gaussian measure restricted to our convex cone gamma. So what does Brenier's optimal transport mapping tell us? Well, the theorem tells us that the transport mapping is the gradient of a convex function between these two measures. So we start with Gaussian measure on Rn, and then we transport using this operator T, which is the gradient of a convex function, onto Gaussian measure restricted to this convex cone gamma that we started with. Okay, where this constant C is chosen so that the two measures have the same total measure, allowing us to carry out this transport mapping. So the crucial property for us is that because gamma is a convex cone, we can think of the measure nu that we're transporting onto as being more log concave than the Gaussian measure on the whole of Rn. And what this allowed us to do was to prove a variant of Caffarelli's contraction theorem, which tells us that not only is this transport mapping T the gradient of a convex function, it has a further property that this transport mapping T is a contraction. Or in other words, the eigenvalues of the second derivative, the Hessian of phi, are bounded above by 1. So how do we use this? Well, applying this theorem, it allows us to use the transport mapping T to transport or transplant test functions on our original cones gamma plus and gamma minus to test functions on complementary subsets in Rn. And then because T is a contraction, when we do this, we don't increase their Gaussian energy. Okay, in other words, we're not increasing those Gaussian eigenvalues that we are caring about when we're mapping between test functions on gamma plus and gamma minus onto complementary subsets in Rn. So what this means is that our Friedland Hayman inequality then follows from the original one, the classical one for complementary cones in Rn. So we get our version by using the work of Beckner, Koenig, and Pfeiffer for the original Friedland Hayman inequality. So that gives the inequality. And then moreover, De Philippis and Figali established the case of equality in Caffarelli's contraction theorem. And what this allowed us to do was to do the same thing in our Friedland Hayman inequality, to establish that we only get equality when the corresponding cone gamma has a copy of R in it. Okay, and I think I'll stop there. Thank you for watching.